So yeah, also from me, a great thanks for organizing this. I think there's two things I really like. A, I met many people whom I knew from papers but never had met before. And two, there were actually many surprising connections, and I hope there will be even more. I'd like to talk a bit about assembly that we do in Germany. I come from INM, which is a research institute for material science in the very west of Germany, exactly at the French border. I'm a professor of physical chemistry at the Saarland University, and we are a non-university research institute on the same campus. My group has been interested for many years in non-polar dispersions, and this is a prototypical one. The picture is from Asaf Cooper, who did many simulations together with our experimental work. Basically, you have some kind of core, which may be semiconductor or gold or something, and you can put, for example, alkyl chains on the surface to make the whole thing dispersible in, say, hexane. And what you get often is mildly attractive. And if these are very short change, which in our case they usually are, then the structure, the molecular arrangement, plays an important role for the interaction potentials between the particles, for the assembly, for kinetic questions. And this is things that we are interested in. We are a research institute that is supposed to do both applied and fundamental research. So another important motivation is that non-polar dispersions are technically relevant. If you want to make composites and so on, very often you're not working in water. Now in this talk, I won't talk about spheres. I'd like to talk about wires. Wires with very large aspect ratios. It is possible for a few materials, maybe for more in the future, to make really thin cores. Here's just 1.6 nanometer of, for example, gold, coat them with a simple molecule like oleolamine, and these wires that grow under the right conditions, in this case, are many micron long. Now, this is drawn as if it was an FCC core. I should already say that this is probably not true. There's recent results that suggest that the cores have more complicated structures, and you also see that the shell is actually thicker than the core. So this organic shell here is dominating the behavior of these ultra-thin nanowires. This has also been simulated. You'll see that later by our colleagues in Saarland, Martin Müser, and it's all my fault. I told him to put an FCC here, which is not strictly correct, I suppose. I'll talk about three different things. I'll first talk about self-assembly. So how do these wires assemble? Why? Under which conditions? What is an entropic mechanism, which is maybe a bit unusual for the assembly of such wires? How can you make hierarchical structures out of them to actually create fibers? Then I'll talk about, maybe the dark secret, or not so dark. There's a stability problem. These wires are so thin that they very easily fragment via Rayleigh-Plateau instabilities. And the question is, why are they stable at all? And we've looked at the role of the shell in this stabilization. And then finally, I'd like to talk about transparent flexible electrodes, because it turns out that you can print these as they percolate very easily, thanks to their large aspect ratio, into electrodes. And I'd like to then end by comparing to wires and asking whether it is better to assemble an electrode out of such wires or out of spheres, using also gold. But let's start with the assembly, and let's look at what happens if you add a bad solvent, a non-solvent, to a dispersion of these wires. This is hexane with not very high concentration of these wires. If you now add a bad solvent, they start agglomerating. And you will see that the way they agglomerate, even at the macroscopic level, looks a bit unusual. It becomes not a collection of blobs. It actually creates this jelly kind of feathery network where these wires, thanks to their large aspect ratio, are all connected. And the trick is basically that bundles form in which these wires are next to each other. This is in the electron microscope. And because they have a very high aspect ratio, the probability of one wire being a member of multiple bundles, of course, becomes very high. So it is very easy to create arrangements where they're all interconnected, which is why we were very interested in these things for electronics or for any application where you would like to have percolation. They do this easily. Now, what is interesting is to look at different solvents and how these wires assemble and in which type of structures they assemble. And Simon Betscheider looked at this in his PhD thesis. This here is small angle X-ray scattering of bundles that formed at certain concentration in different types of solvents just by putting the wires into the pure solvent. I've already shown you what happens if you add alcohols. They bundle. What you now can see in the small angle X-ray scattering is that these bundles actually are densely packed, have kind of a triangular packing. If you look at the cross-section, which is elongated, we can use these reflexes from X-ray scattering to calculate the core-to-core distance, or center-to-center distance. In this case, it's 4.1 nanometers. If you put them in alkanes, pentane, hexane, heptane, they also form bundles. In fact, at this concentration that was used here, they form a dispersion that remains Brownian but contains now smaller bundles. What is interesting is that the spacing here is quite large, it's 5.5 nanometers. As we will see later, that basically means that they are not quite touching. And to our great surprise, if you add these wires to cyclical alkanes, which are physically not so different from the linear ones, but they are cycles, they do not apparently form ordered bundles. And if you do light scattering, look at the larger Q range, you will find that in fact, at this concentration, they don't form bundles at all, which was a bit surprising because we had thought, well, the alkanes should be very good solvents. These linear molecules of the alkanes should be able to fit in here into this shell. Why would they be worse as a solvent? Why would they initiate this type of assembly more readily than these cyclical alkanes, which are different in structure than the linear ones? And it turns out the reason is an interesting entropic mechanism. So what apparently happens is that there is this shell of oleamine, which is here exaggerated as linear, which is not true, a bit kinked in reality. And it appears that these solvent molecules actually form a little bit of an ordered layer in the close vicinity. You can see these layers with small angle neutral scattering. You can also simulate it, as Martin Müser has done it. And if you have two wires, you have these shells. Now, if you bring together these wires, they can share some of these somewhat aligned solvent molecules, and you basically have some kind of depletion mechanism that causes a very, very weak attraction of these wires, but only if the molecules fit in between geometrically. It's a very weak attraction that it causes, and if you had spheres, it would probably not be enough to bring them together, but these wires are very long, so it integrates along their length and keeps them together. If you do this a bit more quantitatively, as Martin Müser has done, you can basically look at what then the spacings are and how the solvent distributes. Here's ethanol. If you have ethanol, you have quite a bit of osmotic pressure pushing them together. So these are the cores of gold, and then these shells, which are really close, and there's no solvent in between. If you are, for example, in hexane, you can now see that there is just a very thin layer of the solvent remaining between them, and yet you get these ordered, densely packed bundles. We can now compare the spacing by just choosing different solvents and looking at the spacing in small angle X-ray scattering, and then we find that indeed the spacing increases as you put longer alkane in between these wires. So it is possible to bundle them through this entropic mechanism with a very gentle attractive potential. You can also be less gentle and do something that is technically very well known. You can spin them. Spinning basically is something that, of course, has been done for hundreds of years. You take something that you can put in a solution, a polymer, and you put it into a bath, a spin bath, in which it's not as soluble. And if you move a nozzle through the spin bath, you can extrude a wire or a fiber, one should say. And we've done exactly the same thing with these wires. This year, it's coming out here, is the wires coming out in hexane in a good solvent, and it's being put now into the spin bath of ethanol, which is a very bad solvent, as you've seen. The wires go together, they form this fiber, which is many micron in diameter, and the fiber that forms can actually be retrieved. It's mechanically strong enough to just take it out, and then you can look at it and check what the wires did as they assembled while they were extruded into the bath. And you find that depending on your conditions, as Beate Reiser has done, you get different structures. So, for example, if you push hard, if you have a large flow rate, if you let the liquid with the wires flow out rapidly and you move the nozzle rapidly, you get this kind of thing, which already in scanning electron microscopy looks more ordered than the fiber that you extrude. If you do this at lower flow rates, at lower speed of motion, then you get something that already at this large length scale looks less ordered, looks more disordered, more coiled. Which is interesting because, of course, in polymers, you also have such effects. Now we see something like this in wires, and we can look at this in much more detail when using, again, small angle X-ray scattering. But because what you can do, of course, is to just use a nozzle that is X-ray transparent and then shine through with your X-ray beam here, push at different rates, and then look what the X-ray scattering tells you about the alignment of these wires. These are 2D diffraction patterns that you get. If you have no flow, if it's a stagnant fluid containing these wires, then these are moving around. They are less bendable than one may think, a bit bendable, but not very bendable, and they just are randomly distributed in an angular way, and you get this perfect circle here. And if you go to high flows, then you are introducing this laminar flow profile, this parabolic flow profile. You have shear. The wires are being aligned, and if these aligned wires now hit the ethanol where they precipitate, apparently they retain this alignment and they form fibers which are more ordered at different length scales than if you put this, well, this doesn't work because there's zero flow, but put this into the spin bath. Does this mean anything for the properties of these fibers? Yes, it does. If you're very patient, you can take the fiber out, let it dry, put it in a little paper frame, and put it in a tensile testing machine. It's not very strong, obviously, so it's a bit of a, yeah, you have to be a bit careful, but you can measure the strength. And you just apply a force and make these classical stress-strain curves. And then you see if you have a well-aligned fiber, the stress at break, the breaking stress is a bit higher than in a poorly aligned fiber, and the strain is lower for these well-aligned fibers compared to a poorly aligned fiber, which makes sense because if you pull at something where you have coiled, disordered nanowires, then you can first extend those, elongate them, as you would maybe do in an elastomer, in a polymer, and then at some point they break, but while you're doing so, of course, they don't resist the force as much as a well-aligned fiber would do, where you're immediately pulling many wires in parallel. If you keep pulling, at some point they will break, and you will see that if you look now at the damaged images. So this is one electron micrograph of a fiber. You see that here, which was ripped apart. And when we first looked at it, it reminded us of failure in either ropes, in hemp rope, for example, which often looks like this. You very often rip out one or some strands, but also tendons, actually. I hope nobody has ever seen that, but if you rip apart a tendon, then also you often rip out strands. And the reason for that is, of course, that these are all hierarchical in structure. And that's also the case for these fibers. If you look at it more closely, you'll find that the way they form is by first bundling at this really relatively small scale of the single wires, which make these densely packed, triangular packed fibers, or bundles, I should say. These then form larger bundles and larger bundles, you may call them super bundles, until you arrive at this fiber with many micron in diameter, depending on which concentration you chose and how large the nozzle was. And this alignment apparently happens at multiple scales. The assembly quality looks the same almost, so at these really small length scales the alignment is not necessary, but then at larger scales it apparently affects how these things are aligned, which then affects the mechanical properties. So here's a way to affect at least one property directly. Now these wires are great, as I've shown you, and I'll show you later that you can make useful things out of them, but they have one big disadvantage, which is maybe also explaining while they are not as popular as they should be. And the problem is that they tend to fall apart. So this is well known for metal wires in general. If you nanofabricate a wire, this here is a gold wire just produced by lithography on a metal surface, and you heat it, then all the microtechnology people, of course, know that it will fall apart and fall into these spheres. And exactly the same thing also happens with the ultrathin nanowires, as many people have shown. This is maybe the simplest experiment you can do. You do transmission electron microscopy, and you look at them for 212 seconds, and they fall apart. I do not know whether, or we do not know whether it's because of temperature, because it's heating, or whether it's a chemical effect or both. But it's very obvious, you look at them long enough, they break apart. It's well accepted that the origin of this degradation is the Rayleigh plateau instability. So basically exactly the same instability that lets a liquid jet break apart into spheres. Everybody, I think, knows this experiment. You open your tap, you close it very carefully, and at some point you will get this transition. And of course, this happens in any system where perturbating this jet or this wire reduces the free energy, and this is going to happen in anything that has a surface tension. And there is well-known scaling laws, so thin wires break faster, and a very thin, ultra-thin wire, as we have here, will simply break at the same temperature in a much shorter time than the thicker wire or macroscopic wire, which a metal wire does not undergo this transition. Of course, the question is also how do the atoms move, and here gold is particularly prone to this because you have a large surface diffusivity of the gold atoms. Now the question is, why do these wires then exist at all? Why does it not fall apart immediately? And the reason for that is, of course, that there is an organic shell on this very thin metal core. This organic shell does multiple things. Most importantly, probably, it's reducing the interfacial energy, which is the driving force of the Rayleigh plateau instability. So it's not as advantageous for it to fall apart. There is multiple other things that it probably does, and it's not known what is the most important contribution. Also, it binds, of course, to the gold. And I've already told you that the FCC is probably incorrect. It even has effects on the internal structure. And it is in that way also making the diffusion slower on the surface, thereby slowing down this instability. Now, what we were very interested in, and it's actually much harder than we thought, was to replace the olyelamine by molecules which would stabilize this better. The idea was basically that if you make a model and you think about how these wires fall apart, somehow to fall apart, they have to undergo a stage where curvature changes. And you can now ask, okay, depending on the molecule that you put on the surface, how can you make it as uninteresting for the system to create such curvature, positive or negative curvature, by looking at the structure of the molecules and changing it, for example. And we collaborated with Norman Fleck and created very simple models, I would say, that just try to quantify this curvature and then create a connection between the change in interfacial energy and the change in curvature. And then you can make plots like this, which just predict that there are regimes, there are theoretical molecules that react to curvature in such a way that you would actually stabilize wires either at small perturbation or at small perturbation or at small and large perturbation, and there are molecules you don't stabilize at all. So theoretically, of course, you could do better. You could stabilize wires by using the right kind of molecule very well, and they wouldn't fall apart. However, historically, many people have tried that, our group and others. There are some reports. So for example, in 2017, a French group reported that a phosphine would increase the stability a bit. I think it at least doesn't decrease it very much, but the difference for us doesn't seem to be very large. We have been able to put a few other molecules on these surfaces, in particular amines. It turns out that if you put thiols, which is the trivial idea probably for a chemist, it immediately breaks them completely, which probably again has to do with the fact that the bond to the gold plays a larger role than one may think. So the hunt is still open. I guess we are still working on this and trying to find whether there's not a molecule that would stabilize these wires further. And ideally, I would like to have one that's also electrically conductive. But it turns out to be actually really hard. There is, however, an effect that you can also exploit, that we do always exploit it without knowing it, and that increases the stability, and that is bundling itself. It turns out that if you have wires that are fully dispersed, they are less stable against Rayleigh plateau if they are in bundles. Experimentally, you can see this by taking a dispersion, say in an alkane, looking at the small angle X-ray scattering and heating it, say to 60 degrees. When you do this, you will see that over time, and you only need 20 minutes, which shows you that it's really not very stable, they are falling apart. You see that the bundles, which create these peaks, don't change so much, but that back here, there is a larger change, and this larger change you can quantify by putting in scattering models, and see that if you have freely dispersed nanowires at 60 degrees, they fall apart relatively rapidly. You are generating spherical or quasi-spherical particles out of that material, and in the end you have a mixture which contains more bundles than as a fraction of overall gold content than before. So it appears that in fact, once you have created these bundles, they prevent the Rayleigh plateau instability to a degree. And you can model this, and it's actually maybe not very surprising, because if you have dense packings, then depending on what you put in as constraints, it is easier, of course, for a single wire to undergo the perturbation that leads to the pinch and the instability than if you have a triangular packing, as we have in our wires. And then all these theoretical packings, which we've never found and nobody was so far able to make, would have different stabilities. So a challenge for further assemblers. This is what we at the moment can really make with one or the other type of lipid molecule. So in these bundles, the wires are a bit more stable, and we've implicitly using this actually for a technological application, which I would like to show at the end, if I have enough time. 5 minutes? Okay, that should be working. Okay, so let's talk about transparent flexible electrodes. What you can do is the following. You take a dispersion of these wires in a solvent. As I said, it's actually better to use a solvent where they already have some bundles formed. You let the solvent evaporate inside the stem. The stem could, for example, have a hexagonal pattern of circles. These wires will form the hierarchical bundles inside, deposit on the substrate if you engineer the surfaces right. You remove the stem, and then you can bring these wires together using sintering steps, which are quite similar to what Rob was showing, so that you convert them into a metal wire. This is what it looks like. Here are the wires. This is a stamp rolling over the wires, and it's quite red because of the surface plasmon. And if you look at the other side, you will see that it's only very bright red because you've created this really thin mesh out of the wires. Here as it comes. It's just a polymer substrate over which it's moving. And this is what's happening. Here's the polymer stamp, in this case, this kind of hexagonal or triangular packing. Wire mesh forms. Plasma treatment to remove the organics, which is very critical because it wouldn't be conductive without that, even though we would love them to be such that they already are conductive before. And then you've created this kind of mesh. This is what it looks like in electron microscopy. Maybe I should have magnified it a bit further. So the structure, this hexagon, this is the stamp, right? The wires do not spontaneously form, I don't know, 100 nanometer or whatever it is, hexagons. That's just the stamp. In each of these lines are many, many wires that formed bundles and which have been now converted into a metal mesh. And what this is basically a transparent flexible electrode, because it's nothing but a very, very fine metal mesh with lots of holes, and they're all, or many of them, electrically connected so that you can use this as a transparent electrode for applications in PV and in other fields. Now, it is also possible to do this with spheres, in fact. This is a mesh in a different geometry that is printed from gold nanoparticles with, I think, 6 nanometer diameter, so a bit bigger than the wires. And it's also possible to print such meshes from spheres. The structures look different. Maybe you see this here. The way they agglomerate, the way they pack and assemble is not at all the same as in these large wires. It's easier, but it's more, you have more risk of not getting percolation. The dynamics are very different. And the question is now, does it really help you to use wires, or is it actually easier and better to just use spheres, because everybody has spheres and not everybody has wires? And Lukas Engel has looked at this in great detail, and there's much more that I cannot tell here, but one thing that you can, for example, ask is, if you take a certain concentration of gold as wires or spheres, and you print electrodes, what is their conductivity as a function of gold concentration? And what is their transmission, optical transmission, say between 400 and 800 nanometers on average in percent? And you can see that these both change with concentration. It's a bit of a confusing plot. Concentration of gold goes up in that way. This is resistance. This is transmission. Because this is confusing, we just invented this figure of merit. Well, we didn't invent it. We just used this figure of merit, which is basically just transmission per resistance. And you see that if you now plot the gold content and you compare spheres and wires, this figure of merit increases more rapidly for the wires than it does for the spheres. So to put it very simple, you could say, according to this, the metal is more efficiently used for the wires, which bring them into a percolating structure where much of it is connected. So that's great. Now, this basically tells that our self-assembling nanowires are very useful. Now, as always, the story gets more complicated the more you look in it. So that's true, but it's only true for, say, a few weeks. Because what also happens and complicates everything very much is that these guys age. So when you now look at a mesh that you've made and you look over many days how it changes, this is the mesh from wires before plasma, sorry. You see actually here some of these parallel bundles, and here in the middle is this thick bundle where it was printed. Now you put it in plasma. Some stuff is already falling apart by Rayleigh plateau. Some stuff is basically brought together into a metal wire, which is more structured than you may want to have it. And then after a few days, it starts reconfiguring and moving and changing. And this aging, in fact, also depends on the structure that you've created in a complicated way. And that complicates the answer because it may well be that if you want a stable mesh, it's actually better to use wires than spheres, even though in the beginning your metal content is less efficiently used. And it depends then on the width of the lines and so on, whether you are better off using wires or spheres. So to summarize briefly, I talked about the assembly of these wires and how they are affected by the solvent type, how you can use this to make hierarchies. I told you about the stability challenge and the chemical problem, which is still open, of putting other molecules on the surface to stabilize them better. And finally showed you that you can make transparent flexible electrodes by simply printing these wires that assemble into a mesh. And I've mentioned several of the PhD students and postdocs who've contributed over the years. This is an old picture of the group. I hope I haven't forgotten too many who have contributed. This year is to acknowledge funding. And I'd like to thank you very much for your attention. And of course, I'd like to answer any question that may arise.
Yeah, I'm a bit puzzled with this proposal of adding ligands that would suppress the curvature, since cylinder, of course, already has a curvature which is way higher than these undulations that are added. Have you thought of polymerizing the ligand somehow so that you sort of form the belt around it, and that would...
So that was imprecise, I should say. The change in curvature they should suppress. Yeah, exactly. But the question is...
can you sort of think of some chemistry of polymerizing the ligands?
Yes, we actually were hoping it would work with the olylامine because it has a double bond. The trouble is, every time we try to cross-link it, it destroys the wires as well. So I think you're right, it's a good idea. People have used ALD to put inorganic layers around it, which works. Organic, we have not been able to find a chemistry that would not destroy the wire and cross-link the shell. But I think that's an interesting idea, yeah.
I have it right here. Right here.
Ah, here.
Sorry. Just first of all, clarification, the wires in the bundle are more or less straight. Is that correct?
Well, the whole bundle, of course, you see it here, right? The whole bundle can bend, and there can always be a wire that kind of goes, I don't know.
Sure, but they're not sort of systematically
No, they're not
twirled
coiled or, no,
okay.
no, not at all. They are much more straight than polymers.
Have you thought about trying to do that, like braiding them, or because there's interesting properties that you get when you can braid wires?
Yeah, so the hope was, for example, that if you would put them in a bad solvent, that they would like coil, like polymers do, but they don't. They are too stiff. Every time, and first of all, they form bundles instead, and then they come out as this big mesh, but they never collapse. So the stiffness is probably just too high, even though it's so thin a gold core. So that's very different from polymers. Yeah.
But there's no way to like twist them while you
maybe there is. I mean, it would be really interesting. It would be great to coil them up so that they could then later release but yeah, we haven't managed to.
Thank you, Tobias. So we have a very similar growth of nanowires and rods of zinc selenide using oleolamine as well, also very thin. So first, the first question is the mechanism of growth, if you can comment about that. And the second question, then the mechanical properties and so on. To what extent is this dependent on the core or really more determined by this organic template or shell?
Yeah. Maybe the second question first. So I think the stiffness comes from the metal core, because, I mean, how would the shell create something that's stiff? And you see that they're relatively stiff. However, the instability apparently is really very much a combination of the core and the shell. And of course, it's mediated by transport of gold on the surface, which depends on the gold itself, but also on how the shell is sticking to it and how it's bound and so on. So there I would expect large differences depending when you are able to put something on that also sticks on it. It's very interesting that you say this about the semiconductors, because they should be much harder. So we've been trying to make wires, and maybe I should just talk to you and learn how to really do it well. Because there I would expect that you don't get the Rayleigh plateau instability there as easily, most likely. And also I would assume that this bond and the actual organic gold contact or the organic inorganic contact is not as important for the properties as they would be in gold, but that would be very interesting to compare. Now for the formation mechanism, yeah, there's many ideas. This one is the one here that at least the PhD student thought was most likely to actually happen. So here the idea is that you have first some kind of gold chain formation, which then starts forming clusters, and the oleolamine is always around, and then you have sideways growth. And the claim is that this kind of chain formation also leads to the deviation from FCC. I don't think that it's really known yet, and there's different ideas that still compete, but yeah, I mean, there are some structures where it's really very uniform along the length in the thickness, which already excludes many proposals, in my opinion. However, also this one, it's interesting how maybe it's like a very long cluster, and the actual internal gold structure has some kind of magic configuration that geometrically prefers very much in a certain thickness, because it's also not possible to grow them to any thickness you like at all. You get a certain thickness, it's reliably the same, and you cannot vary it.
Thank you.
I have a quick question here. Do you know what is the stiffness of these rods? And they're made out of gold, and if you just put this under optical microscope, they should be really, if they're several microns in length, you should directly be able to observe the bending fluctuations due to the finite size stiffness. Do you know if anybody's done anything along these lines?
Yeah, so I think in optical microscopy it's very difficult to see a single one directly, but people have done light scattering, no?
No, with optical microscopy, these things should light up like crazy. You can see a 20 nanometer gold particle.
So I don't know of anybody who has seen single ones in optical. Maybe it was just not trying hard enough. What people have tried is light scattering, and to see whether you can reconstruct this fluctuation. Basically, the people were more interested in the length, in getting a reliable average or distribution of lengths. And so there is data. We haven't done that. And I mean, I agree with you that if it's I mean, actually a 2 nanometer diameter gold nanoparticle is not so strong in dark field scattering, right?
If it's long enough, you can see a protein that's 20 nanometers in diameter.
Just by the length, yeah.
Yes.
And then the question is whether you could see so we haven't tried that.
So I have a question regarding these three situations with these three different solvents. Can you put the...
Yeah, of course.
So what you see here is when the solvent is aromatic, you don't get bundles.
It's not aromatic, it's just cyclic.
Cyclic, sorry.
It's just an alkyne.
Okay,
alkyne.
so cyclic. And so what is the argument why that happens? I couldn't follow that.
So the argument is if you have linear alkanes, then you get solvation by a shell of the molecules which are sticking in here and are somewhat aligned around the wire. If you have these guys, these have a complicated chair-like conformation. They are not at all linear. They are not aligned, or they do not lose as much configuration entropy by being interacting here. So therefore, if you put these in, the gain that the wires have by sharing a solvent shell is not as high as for the alkanes. And so this entropic mechanism of attraction is much stronger for alkanes than for cyclical alkanes.
I see. Okay.
So basically this doesn't work, right? If you try to fit in cyclical ones, that won't work. The linear ones, however, can arrange in between the wire shells.
So basically what you are saying is that the cyclic ones cannot penetrate there.
They don't fit in, yeah, they don't go in.
But then, okay, I mean, but then they would kind of generate some kind of depletion interaction. I mean, it's not an easy question. But
Yeah, it depends on, yeah, exactly, yeah,
But,
yeah.
Maybe I can ask. Hi, Tobias, here.
Sorry.
Yeah, thank you for a very nice talk. So, since you kind of exposed to both applied fabrication techniques and also fundamental research, I wonder if you have any insight on sort of what specific advantages self-assembly adds to this fabrication that you cannot achieve with other techniques. Like, why would one want to work with this, messy, like wires and liquid samples instead of using some printer or some sputtering device?
I mean, here the argument is very simple. If you're using, for example, this printing process, right, what you want to have is essentially all the material going into one line, ideally much more narrow than even the feature that you're printing, rather than distributing in some unknown fashion. So the perfect self-assembling system would make sure that everything is connected in this one block, which you can then later convert into one metal block, and then ideally also would be stable against degradation later and so on. And if you just use if you would use something here, which, yeah, you can also do that during evaporation, is too repulsive, it just will distribute everywhere, right? And you will get something which later is not connected and you're wasting all your material. If you have your spheres, well, they already, if you do it right, go together in a line, and most of it is at least somehow connected, even though the profile is maybe not ideal. If you use the wires, they are collecting, because of this percolation tendency, the material even more in something where everything is interconnected. So that's, to me, for such an imprint process, a useful property of the dispersion that you are printing.
Thank you.
Yeah, hi, amazing work here. So I have two questions. My first question is for the wires. I'm actually thinking about polymers. So when it comes to polymers, one way to really show their flexibility is the measure of persistent length. So do you have a similar measure of that to your wires?
Yeah, what you can do is just, I mean, there are very simple models where you just take a stiff beam, or you put in the elastic modulus of gold, and then you can calculate what the basically persistence length is as this thing bends in a Brownian fashion. Then you should compare it to a measurement like you, and then you would probably find that the gold is not as stiff as expected, or maybe stiffer. I don't know, that's very unlikely, but that would be very interesting also to answer the question of the organics. So we haven't done that. There is this light scattering data, which I think isn't very conclusive, but what seems to be the case is that they are more stiff than you would imagine. In the old days, we were always drawing these like polymers because people thought they were like, but that's not true. It's really relatively stiff as compared to a typical polymer.
Yeah, that's great to know. And my second question is when you wave the wires into bundles, you show this demonstration that you draw a line. Can you actually do that in 3 dimensions?
Yes, but then you have to do it in the gel, for example, like people of course have done, because otherwise it will just sediment and lie down right onto each other, because it's relatively heavy. If you were, the density is so high that it will just fall down.
I see.
But you could draw it into a gel in principle.
I see. The reason why I was thinking about that is because yesterday Xiaomin gave this wonderful talk on mechanical metal materials. Usually those are made out of frameworks. So I was wondering if you can actually print out a framework in an arbitrary shape, which is actually not easy to make using self-assembly.
Yeah, so actually we've been trying something in that direction more using rods, which also align. But you're right, this one has probably a more direct effect on mechanical properties. So I think it would be interesting to be, but to be fair, of course, you can also do this with polymers because they also depend, the mechanical properties don't change as much, but they also depend on how you shear them in, or there are systems where it depends on how you shear them during extension.
Thanks.
Or composites.
Hey, Tobias, I have a follow-up question to Alex's question about the solvent layer between the wires. So you showed some simulation results there.
Yes.
I was just wondering if they showed in these simulations that the potential of mean force actually has a minimum at that distance.
Yeah, so now this is probably a question for Martin Müser actually, and I'm not sure whether I have the potential of mean force here. Yes, they did, but I don't have the data here.
Okay, so there is actually...
That's the idea, that this is an equilibrium distance that they're actually finding. Yeah, exactly.
Oh, it's interesting, thanks.
I have a question also about here.
Yes.
About this entropic agglomeration mechanism.
Yes.
Now, if I got it correctly, the idea is that you have some release of solvent molecules, so the entropy of agglomeration is positive, right?
Yes.
So I was wondering if you did any measurements as a function of temperature, because that will give you, because the agglomeration entropy is positive, temperature should favor agglomeration.
Yeah. The trouble is, so we have done temperature-dependent measurement. The trouble is, if you do this with oleulamine, it is dominated more by the absorption-desorption equilibrium of the oleulamine on the gold wire, and then by Rayleigh plateau. So I think the difficulty was, so there is data, and I'm not sure whether it's in the paper, because the problem was always to differentiate between both. Even if going to moderate temperatures, above room temperature, there was already quite an effect on dissolving more oleulamine, which also has a relatively strong effect on, so this is why we, in the end, try to keep all on one temperature and not do it in a wide range. But yeah, of course, it's a good idea in principle to look at whether it's entropic just by temperature dependency. Yeah. So there's another paper on this question where if you dissolve these oleulamine molecules, they also do something, of course, because then they are in solution and they're also starting to interact with the wires. At the same time, you're making less dense of a shell around the gold, so that has an effect as well.
Do they form a liquid? Can they form a liquid crystal in a good solvent?
Nobody has reported that, so I do not know. We've tried to make very highly concentrated dispersion. Yeah, I do not know whether this, we have never been able to identify one, whether it exists, maybe.
For those grids that you were doing at the end, sorry if this is naive, but it seems like you could probably do a lot with those, but are there like specific things that you have in mind that you can do with those grids that you couldn't otherwise?
Yeah, one thing you can, I mean, of course, there are many types of transparent conductive grids, and people are making them with microfabrication all the time, right? I mean, all the touchscreen displays are based on them. So one thing we were interested in is perovskite photovoltaics, because the gold is not going to interact much with the perovskite, was the hope, so it would be an interesting alternative transparent electrode, but also actually transparent touchscreen systems which you could fold around or bring onto curved surfaces are an interesting one. And I'm also very well aware that there are a number of companies who try to do similar things with silver nanowires. Not all of them survived, regrettably. So yeah, there's also competition, of course.
Okay, thank you very much for the wonderful talk and all the questions. Yeah.